Okay, I've given you back your tests now. Remember, I had them graded right away, but we had 2 people who didn't take it with the rest of the class, and I had to wait for those to get graded. And those 2 didn't get back their tests yet. Don't get them back soon. So now you can look over. If I did not grade yours by hand and you wish it to be graded by hand, that is the last 3. Just give it back to me and tell me. For most people, I did already grade them by hand. If you have questions, or like Mira already probably saw came up and I made a mistake on hers, bring it up with me. Don't say, oh no, what he did, and I can't do anything. Because we want to make sure that you're happy, that you understand what you got, and so on. So I won't ask if there's any questions about the test. You haven't had time to digest that. Instead, I'm going to get into today's lab. Now, today's lab is probably the longest one of the semester. Yeah. And I have to start by lecturing on this material so that it takes you less time. So what we're going to be dealing with is AC circuits. A circuit that has an inductor. L is the symbol for inductance. We just got into the topic of inductance in class yesterday. We talked specifically about transformers, which are mutual inductors. You put a current through one coil and you get a voltage coming out of the other coil, is the way that's easy to talk about with Faraday's law of induction. An inductor is short for a self-inductor. A self-inductor is a single coil. So once again, I'll use my slinky as an example. If the slinky was insulated, then the slinky would be a self-inductor. If I put current into the slinky, it creates a magnetic field. And if the magnetic field changes, then it's going to induce an EMF. But it's inducing an EMF in the same wire that the original current was. So that induced EMF is sometimes called a back EMF. So in your homework problems that are going to be due tomorrow, you're going to have some problems that ask you about the back EMF. To find the back EMF, you simply say, okay, I have this coil. I have a current that's going through it that's changing. That changing current then is going to induce a voltage. What's that voltage induce? So inductors respond to changing current to give you a voltage. Because the inductors respond to changing current, if you have a sinusoidal voltage, so this purple line is going to be our, sinusoidal current, let's say. So the purple line, which is showing the voltage through the resistor, since voltage through resistor is I times R, the current is proportional to that purple line. And where is the purple line having the biggest change in its value? Where is it changing the fastest? That is, where is the slope the steepest? Okay, at 0 is the biggest, steepest positive. It has the steepest negative out here at 1/2 t, steepest positive again at t. And so those are the places where we are going to have the biggest induced EMF. So those are where we're going to have maximum and minimum voltage across the inductor. And so if you look at the green dashed line, that's the voltage across the inductor. And you see the inductive voltage is the biggest at the time when you had the positive slope. Because of the way we identify directions. Then with the capacitor is storing energy. Well, let's back up. How does the inductor store energy? It stores it in the form of what? The inductor, it's a magnetic field. And so when you have the strongest current, you're going to have the most energy stored. So when the current is the strongest, at this point, you have the most energy stored. And then it's going to start returning energy as you go past there. Now with a capacitor, what does it store energy in? Well, charge separation or voltage, and the potential difference relates to that as well. So it's not bad. So the capacitor stores energy in charge separation or electric field. Well, when the current is 0 is when you're going to have the maximum charge. And so when the current is 0, which is right here, I have the maximum charge, right? We've been adding charge all this time. So here we're at maximum charge, so the voltage across the capacitor is maximum there. And then we start pulling current away, and here we're going to have the minimum charge, and hence we have the minimum voltage on the capacitor. What's really important to note here is that you have the inductor reaches its peak voltage 90 degrees before the current reached its peak. The capacitor reaches its peak voltage 90 degrees after the current reached its peak. So that you have different times where you have the peaks for the inductor, resistor, and capacitor. That's one of the things that's weird about an alternating current circuit, an AC circuit. You have different times when you have your peaks. You've learned Ohm's law. V equals IR, right? You should have that down cold. For a capacitor, we have a relationship that said Q is equal to VC. And so if I take delta Q over delta T, that should be delta V over delta T times C. But delta Q over delta T, that's the definition of current. So the current through the capacitor is equal to the rate at which the voltage across the capacitor is changing multiplied by C. That actually gets us to the words that DJ used when I asked about when we, I forgot what my question was, but you said voltage. This equation here that agrees with what you were saying. So we have a relationship for the current through a capacitor is equal to the capacitance times the rate at which the voltage across the capacitor is changing. If you have a sinusoidal function, doing some calculus, the rate at which the voltage is changing is going to be the angular frequency omega multiplied by cosine of omega t. For the inductor, the induced voltage was the inductance times the rate at which the current is changing. Once again, with calculus, you're going to have an omega t aspect there. And so we can make Ohm's law equivalents for all three of these devices. The maximum voltage across a resistor is the maximum current times the resistance. The maximum voltage across a capacitor is the maximum current divided by omega c, where omega is the angular frequency. And the maximum voltage across an inductor is maximum current times omega L. And so we have three forms of Ohm's law, if you will. And because 1 over omega c fills the same position as resistance, we say the reactance for a capacitor is 1 over omega c. That reactance is measuring the equivalent to resistance, except a resistor takes away energy. A capacitor stores it and returns it. So we don't call it a resistance because it's doing a different thing with the energy. It's returning it. For an inductor, the equivalent to resistance, the reactance of the inductor, is omega L. So this reactance, how they react, if the frequency is high, which one of these devices does virtually nothing? If omega is large, which one does basically nothing? Okay, if omega is very large, XC becomes approximately 0. So a capacitor behaves basically like a wire at really high frequency. We say, sometimes you might hear people talking about high pass and low pass filters. A capacitor would be a high pass filter because it's going to just allow current to go right through at high frequency. Well, it depends on how you put it in the circuit. You can make high or low with a capacitor. But if you just have a capacitor in series, it passes high. At low frequencies, your X sub C is very large, so it's going to block current at low frequencies. The inductor, on the other hand, at high frequencies, it blocks current. But at low frequency, it just passes current. This actually makes real good sense because an inductor is a wire that's just wrapped in circles. At low frequencies, it just behaves like a wire. But at high frequencies, you start making magnetic fields that interfere with the passing current. The capacitor is two plates that don't touch each other. At low frequency, you have an open circuit. No current goes through. But at high frequency, you have the energy being stored and passed back and forth that makes it behave more like a wire. So we have the equivalent of Ohm's law using reactances. We have to remember what we saw from this picture, that you have these peaks are not at the same time. The peak voltage across the capacitor is going to come 90 degrees after the peak voltage on the resistor. Whereas the peak voltage on the inductor is going to come 90 degrees before the peak voltage on the resistor. And in fact, if you look, the peak voltage on the inductor corresponds in time to the minimum, the negative peak for the capacitor, and vice versa. So how do we use these in a circuit? Well, we're going to be using that today. One thing we do is, well, we're going to measure the voltage drops across each one. In your experiment today, you're going to make these voltage measurements. You're going to measure the voltage across the source. You're also going to make voltage across the inductor, and we're going to call that L plus lowercase r. L plus lowercase r, because an inductor, it has a wire with some real resistance. Moreover, I talked in class yesterday about what's happening if you put a core, that is, if you put like a piece of iron in the coil. That iron is going to align with the magnetic field, making the magnetic field much stronger. But in doing so, it takes away some energy because there's some work required to make it align. And so since there's energy taken away by making the magnetic field, energy with AC current going through an inductor. And since you lose energy, that looks like a resistance. And so that lowercase r is representing the resistive part, or what looks like a resistive part of the inductor. So that's why that's called V sub L plus R. Then you're going to measure V sub R, V sub C, and one more. V sub L plus R. So you're going to make 1, 2, 3, 4, 5 voltage measurements. So when it comes time in the experiment to make these measurements, I want to be clear what you're measuring. Then you're going to make some phasor diagrams. A phasor diagram means that we are taking a vector. Well, is voltage a vector? No. But we're taking that voltage and we're treating it like a phase vector. I went back and forth and erased, of course. And so we have the voltage relationships that said that the voltage for an inductor is peak 90 degrees before the current. The voltage for a resistor is peak 0 degrees before / after the current. And the voltage for a capacitor is peak 90 degrees after the current. And so what we do for a phasor diagram is we say, okay, let's look at, for instance, the voltage. And then let's say it's at an angle. So voltage for an inductor would be the voltage you measure at plus 90 degrees. And so we're just going to make a diagram, and we will plot inductive voltages like that. Actually, much quicker to do it this way. So we're going to plot inductive voltages at plus 90 degrees. And then we're going to do capacitive voltages. Voltage for a capacitor is equal to voltage at minus 90 degrees. So capacitive voltages are going to go like that. And resistive voltages, since they're at 0 degrees, go like this. So we're going to plot our voltages with a direction and then add them like vectors. The reason we're doing this is because they have their peaks at different times. And the way this is really supposed to work, if you look at pictures, you usually see this tilted instead of just horizontal and vertical. Because with time, the directions are going in a circle. And you take the horizontal component, and that's what the voltage at any instant is going to be. So at this time, the voltage across the inductor and capacitor would be 0, and the voltage across the resistor would be positive. But if you wait a little bit so it's tilted, the voltage across the resistor will drop, the voltage across the capacitor is becoming positive, and the voltage across the inductor is becoming negative, because you're taking the horizontal aspect. So what you measure with a meter is just measuring the horizontal aspect of these, and it's rotating in a circle. Does that make sense? It's
the circle doesn't.
Okay, the circle doesn't as much. Okay, so let's just take one. I wish I had an option with this tool to rotate a picture. Here's my voltage across the resistor in an AC circuit. At time equals 0. But at some time later, the voltage across the resistor is going to drop because the current has dropped. Well, what we're doing here is saying if I take this picture and sometime later I take a line with the same magnitude, but it's now rotated, so this angle is equal to omega t, then the amount that I have in this direction is going to be VR cosine of omega t. And so with time, my voltage is going to go from positive VR to negative VR back and forth. And if we take just the horizontal projection of this arrow, the arrow goes like, magnitude is staying the same, but the angle is moving. And okay, so the magnitude is the same. All those arrows are supposed to be the same length. I realize now they're not. And so depending on what angle it's at, the amount you get in the horizontal direction goes from positive, going smaller, to 0, getting bigger, negative, getting smaller, back to 0, then coming back to positive. So that's just looking at the resistive part. If you look at the inductive part, it's always going to be 90 degrees away from the resistive. So it starts at 0. It's going to negative as the resistive one comes down. And so when the resistive one is 0, the inductor is at its maximum negative. And then, okay. My flexibility ended. But if you keep going, then you're going to have the resistive one becomes negative and the inductive one goes back to 0 until the resistive one's like this and the inductive one's like that. Resistive, inductive. You get to like this, the resistive is at 0 and the inductive is positive. It's 90 degrees ahead, so the inductive reached its maximum before the resistive does, and we're back to where it started. hands is not the best way to do that unless you're some kind of crazy flexible. Does that make more sense on what the phasors are representing? Does to DJ. If you have questions, ask DJ. Thanks, bud. So we're going to use these phasor diagrams in our work. So next thing, how do you add vectors? Well, you add them tip to tail. How do you find the magnitude? Well, use the Pythagorean Theorem if you have perpendicular components. And so we can find, for instance, the voltage is found by taking the resistive voltage squared, right? That's the horizontal component here. I should draw this a little more carefully. Notice we have the voltage inductor here is a big positive. Voltage capacitive is a small negative. So if I put those together, my vertical part is voltage inductive minus voltage capacitive. And then the horizontal part is the voltage resistive. And so using the Pythagorean theorem, this quantity here squared plus this quantity here squared is equal to the resultant squared. And so then I just square root and I have that resultant. The voltage across the entire circuit in this case is equal to the square root of VR squared plus parentheses VL minus VC quantity squared. Question?
So the point of all this is to ultimately figure out what the total voltage is in a circuit.
There's a lot of different points. It depends on your goal. So that is the point of this calculation here, yes, is to be able to go from the voltage across each of your individual components to the total voltage. You don't just add VR plus VL plus C. Why don't you just add VR plus VL plus VC?
Because VL and VC are in opposite directions.
Okay, opposite directions in the phasor diagram because they're at peaks at different times. If at any instant you add up VR plus VL plus VC, it's going to give you the total voltage. But we're just measuring the peak voltages in our experiment. And if you just measure the peak voltages, they're not all peaks at the same time. If you just try to add them, you're trying to say, well, the voltage at this time was this, plus the voltage at another time, plus the voltage at another time. Well, you have nonsense at that point. So you can't add all of the peaks together to get the total. You have to take them at one instance or use the Pythagorean theorem here, knowing the phase relationships. Last thing before we look at the lab specifically is impedance. Now I talked about resistance. Resistance is physically resisting the charge going through, taking away energy as the charge goes through. Reactance is reacting to charge going through, storing energy and giving it back. So a reactance, that would be a capacitor or an inductor, has a reactance. They don't take away energy, they store it and give it back. So the average power for an inductor is 0. The average power for a capacitor is 0 because they're only storing energy and giving it back. Whereas the average power for a resistor, that's not 0 because it's taking away energy. We can take these resistors and inductors and capacitors, reactances, and we can combine them to find what we call an impedance. Impedance is anything impeding charge, whether it's resisting or reacting. And just like what we did with the voltage, we can take the voltage relationship using the Ohm's law equivalence. They all have an I in there. So you factor out the I. The total voltage over the total current is going to be what we call the impedance. So this is a fourth version, if you will, of Ohm's law. The voltage is equal to the current times the impedance. And then that impedance, just by following the work, is square root of resistance squared plus XL minus XC quantity squared. Now, something cool about this is, if I have a circuit with a resistor, an inductor, and a capacitor, if I change the frequency, my XL and my XC are going to change. Remember, XL is omega times L. XC is 1 over omega C. So as frequency goes up, XL goes up and XC goes down. That means there's always going to be some balance point, some frequency where XL equals XC. If XL equals XC, then Z is equal to R. For any other frequency, Z is going to be bigger than R. And so you're going to have a minimum impedance when XL equals XC. That minimum impedance means you're going to have maximum current because V equals IZ. Maximum current, we're going to measure in today's experiment by measuring the voltage across the resistor, since voltage across the resistor is just IR. And so we call this the resonant frequency, the frequency when you're going to have the biggest voltage drop across the resistor. How do you get that? Well, if XL is equal to XC, XL is omega L, XC is 1 over omega C. I'm going to put subscript zeros on the omega because it's the resonant one I'm looking for, right? Because my equality is only at resonance. Well, let's solve this for the resonant frequency. How do I solve that for omega 0? Not length, but inductance. And so then what I have is omega 0 squared. Can you read that? Yeah. It actually is easier to read there than it is here for once. Equals 1 over LC. So omega 0, the resonant angular frequency, is 1 over the square root of LC. Now remember, omega is equal to 2 pi f. So frequency is equal to omega over 2 pi. So resonant frequency is equal to 1 over 2 pi square root LC. So you're going to find L for your inductor using the relationship for the frequency and impedance for the inductor. Find C for the capacitor. Once again, using that relationship for XC. Then you're going to calculate what the resonant frequency is, and then you're going to experimentally measure what the resonant frequency is. Let's need to go here. Here's a graph showing what it looks like if you plot this is current, but we're going to do voltage through the resistor as a function of frequency. And depending on the value of your resistance, it may be more of a peak or less of a peak, but you'll have a peak. Something to note here is that this is a logarithmic scale. If you plot it with a logarithmic scale, it will look symmetric. If you plot it with a linear scale, it's going to be stretched out like this instead of looking symmetric. So with that, I should come back to it. There's one more thing. Power factor. Because you have a circuit containing resistor, inductor, and capacitor, the total current may not be in phase with the resistance. Or in phase with the voltage through the resistor. Said that again. Well, the total current may not be in phase with the voltage coming out of the power supply. The power supply can have its peak current at a different time than it has its peak voltage, which seems weird. The power company is charging you for voltage times current. That's all they really can do. They're delivering voltage at a certain level, and they measure how much current is going into your house, and that's what they charge you for. It's voltage times the current, multiplied by time, of course, because they're charging you for energy. But an inductor or capacitor returns the energy. Where does it return it to? The earth. Power company can't recover that. So it's not like they're going to cut you a break and only charge you for what you use. They charge you for what went out of their system into your house. And so if you have something that's a pure inductor, something like a fan is just an electric motor, which means you have a big old coil, an inductor, and you put electricity through it, and because of the external magnet, it makes it rotate. So the fan uses virtually no energy. It uses some energy to get started, and of course there's a little bit of energy to keep it going, but it's not using very much. But the current it's using is pretty high. And so the power company is just charging you for the current times the voltage. But if you can put a capacitor in there, you can change the phase angle. You can make it so the current comes back so it's in phase with the voltage. And in so doing, you're actually going to lower that current and get charged less by the power company. And so we have this thing we call the power factor angle. So right here, cosine phi is the power factor. Phi is the power factor angle. And you find that by taking the total resistance that you find, total voltage you find with the phasors and measuring what angle that is from horizontal. So you're going to measure that as well. So I'm going to summarize here what your results are going to be. Remember your results section. It needs to be succinct restatements of things you found in the experiment. Nothing new here. You're going to have the value for the capacitance and compare it to what's marked on the capacitor with a percent error of difference. So you'll say, I found my capacitance to be this. It was marked as this, so I had this percent error of difference. Likewise, for the inductor, what's marked and your percent error of difference. And then you're going to have the voltage total compared to the voltage total you found, well, let's put measured, and from your Phasor diagram, and the percent error of difference. The resistive portion of the inductor, you don't have anything to compare that to. And then you're going to have the power factor angle measured, from the graph. And finally, resonant frequency calculated, resonant frequency measured, and the percent error of difference. Those are the things you're going to have in your results. So you need to have those 6 things. Notice your grader's taking a picture so he knows when he's going to grade. Now let's look at the actual instructions. At this point, you're pretty much ready to roll, but I want to make sure we do go through the instructions. There is no scientific method aspect to this one. Again, it's just too complicated for you to have to do a scientific method. Your final graph, you're going to make 2 graphs. The first graph is going to be this one here, where you're finding, the purpose of this graph is to find what the resistive portion of the inductor is. So you know that the voltage difference across the inductor plus resistor, you measure that. And so you take a compass. This needs to be like a half sheet of paper. I want big graphs, okay? And you take the compass and you carefully set the compass so its radius is scaled to be equal to the voltage drop you measure total across the inductor and resistor. And you draw that quarter circle starting from the origin. And then because our phasors should add as vectors, you put the voltage you measured across the resistor starting at the origin horizontally. And then at the end of that, you know you have the voltage that you measured across the inductor, the V subscript L plus R. And so you set your compass to be the length for that from the end of the voltage resistor, you draw that arc, and where the two intersect is where you have voltage across the resistor plus voltage across the inductor is equal to voltage across both of them. So that's what's being indicated here. The green is the voltage across both, the blue is the voltage across the resistor, and the red is the voltage across the inductor. The point of that is then you can measure, because you had carefully scaled, you measure how big this voltage drop across the resistance part of the inductor is. And you measure, so you measure this horizontal distance. That was a bad color to use. You measure this horizontal distance, and that's the voltage drop across the resistive part of the inductor. You measure this vertical distance, and that's the voltage drop across the inductive part of the inductor. Once you have done that, then you can calculate, first of all, what the current is through the circuit by just using Ohm's law with the resistor. And then using that, you can calculate what the little resistance actually is from the voltage you measure for the resistive drop on the inductor, what the inductive reactance is, and what the capacitive reactance is. Then using your frequency, you can calculate what the inductance and the capacitances are. So I'm going to now look at this more carefully. First thing you need to do is set up your circuit as shown here. So this one here is already set up for me. That is, it has a resistor here. The resistor goes into the inductor. Resistor needs to go to the inductor because you need to measure the voltage drop across resistor plus inductor. So it goes from the resistor to the inductor, comes out of the inductor here, then it has a capacitor here, and then I'm going back. My power supply is this right here. So the power comes out of here, goes through the circuit, comes out. And then I'm going to use a probe, voltage probe, so this here, to measure each of my voltages. So I am going to quickly, I hope, run through this. I should have loaded this up beforehand. We did it, but that doesn't seem to have started up. I probably am going to have it pop up twice here when it does. Wait for it. And, well, so far so good. Plug this into here. You need to open up, of course, the experiment for today, which is a different location for me than it is for you. Yeah, wrong class. Hopefully, no, I'm not going to have here. It's got to be. Come on, lab guide. Okay, so it's lab 14, AC Impedance. And there's a couple important things to note. Now it's going to come up and it's going to show an oscilloscope view, and you see there's a bunch of lines on there. There's a bunch of lines because that's what I saved it with. I had a bunch of these connected. I do recommend that you start with like 3 of them connected like I have. But when you do your actual measurements, you need to disconnect 2 of them because they will interfere with your measurements and give you bad data. So I'm starting with 3 of them, and with 3 of them I can see that I have my source voltage was the red, voltage across the resistor was the blue, voltage across the inductor was, well, the one that's a little bit bluer of the green, and across the capacitor, the one's a little bit greener of the green. So now I'm just taking these out so that I don't get confused with them. And I'm going to measure the voltage across each one of my items. So right now, let's disconnect I got to make sure I disconnected the right ones. Right now, I just have the power going through the circuit. And actually, Andrew, why don't you come up here? You can, I'll give Andrew the easier of the two jobs this time. Go ahead and control that. So one of the things that you need to do is first, with all three connected, adjust the frequency. Show them how to adjust the frequency. See over here where it says signal generator on the left? You click on that, and now it shows you the frequency and the amplitude. Go ahead and leave the amplitude at 10. It says 60 in your lab guide. Just leave it at 10. And then you can adjust the frequency just by changing that number. And by the way, see where it says sine? We do need to have it at sine wave. So we changed it to 300. Now, if you go down to the bottom, there's a problem. It does not lit up. Well, click on monitor. It should work when you click monitor. I don't think it's going to because it's grayed out.
It didn't work.
Click on hardware setup. Yeah, it doesn't see it. It's connected. Okay, maybe we won't show you. Come on, baby. Come on. We were using the computer instead of my... well, you see, as long as it has that yellow triangle, it's not going to measure any data. I mean... Oh, I know what the problem is. Remember, I started it twice. There's going to be a second one of these. Need to close that one. That's what the problem is. Hit cancel or whatever. I get later, remind later. And then we need to close this. Yeah. Okay. Now, that should work. Okay. That's what happens when you have two instances of the software running. Okay, so now if he clicks monitor, it will take data. And what you see there is my voltage across the power supply and nothing else. Now, one thing you can do to make life a little easier is see up there on the top where it has a 1. Click on that, and then it's just going to take one sweep. That way you don't have any little shifting to worry about. And so we can measure right now what's the voltage of the source. So go ahead and turn on the tool there.
Which one?
Over to the 2 more. That one. Okay, so that's the tool for measuring. Then you just take that and you drag it over to the peak. It will actually show an arrow. It's actually easier on it shows where it's measuring and the voltage. So where he has right now is 9.924 volts. Now, one thing to do is to try to make sure you're at the peak, which is kind of hard to do, especially with the touchscreen. He's a little bit before the peak, but with the touchscreen, it's really hard to be correct. Yeah, there he's got it pretty close to the peak. Now you see it went up a little. So here we have the voltage for the source. Now I'm going to plug in my voltmeter across the resistor and just click the monitor button. And hey, what's up? It totally disappeared. Turn off the one shot just so we can. And then click monitor again.
There we go.
There we go. Okay, so now click it back to one shot. Hopefully it was just a fluke there. Okay, and so now, of course, right now that's looking at the power coming from the source again. You need to shift to the power across the resistor, or the voltage, excuse me, across the resistor. So he just takes his tool and drags down to the resistor line and tries to, now notice it shifts one to the other, so you have to be a little careful on which line you're looking at and get it to the peak. Notice that the time where I have the peak for my power supply is not the time where I have the peak for the resistor. They're different times. That means that the current is not in phase with the voltage. So we have here 4.145 volts, good job, for the voltage across the resistor. Now I'm going to go to the voltage across the inductor and repeat. And so now the inductor, oh yeah, you lower the frequency. I was like, that's not what it was yesterday. So no, that's the source. You can always tell by looking at the legend up in the top right. The one that's kind of magenta-ish color is the one that we're looking at with our probe. And so we have 4.782. And then we go to the capacitor, which is going to be from there to there. And let's measure that. So the capacitor here is now the pink one. And so he's going to drag that up to measure what it is at the peak of the pink one. And once again, you got to cut them or break. It's hard with the touchpad. So we have 12.927 volts. That's a larger voltage across the capacitor than we're putting into the circuit. How is that possible?
It stores some voltage.
It's storing energy, and it's got a positive voltage when the inductor has a negative voltage. And so the sum of the positive capacitor voltage and the negative inductor voltage, that's going to come out less than the voltage we're putting in. So you can actually get a larger voltage than you put in because it's not at the same time. We've measured all but one of our voltages. What's the last voltage I need to measure? I need the one across two elements. The resistor and the inductor. So last one, resistor and inductor. We go like that, do the last one, and it's the low one. And so there we have all of the measurements that we have to make. Now, one thing, remember I said, when you make your measurements, use only one probe. But I recommend you start with 3. Why start with 3? Well, let's go to the 3 so you can see. Where did I put the other 2? I just stacked them with the others because it's not that way. I'm going to put these in and measure the voltage across the resistor with the first one. The voltage, come on, you're stuck together now. Well, that's fine. The voltage across the inductor with the second one and the voltage across the capacitor with the third one. Now, like I said, this isn't going to give us actually good results. It will look good, but it won't be right. So now we look at this, and you have to choose your frequency. And you have instructions on how to choose the frequency. It says, and I'm going to quote, adjust the frequency generator until the voltage across the inductor and the voltage across the capacitor are both over 4 volts, but not equal to each other. So I look up here and I say, okay, they're both over 4 volts. They're not equal to each other. One is 10 and one is, actually it might be under 4 volts. So what do we do then? We change the frequency. This one here, we know the frequency is going to be good at 400. So go ahead and put it 400 so they can see the difference. So it puts it 400 volts and we measure it. Click back on the graph. Something's definitely missing on the graph.
There we go.
Okay. And so now we see the inductor voltage there is about 8-ish. The capacitor voltage is about 13. The resistor voltage is about 6. We want to make sure that we have our voltages are all over 4 volts. Well, the resistor voltage, it says, needs to be over 2 volts. If the resistor voltage is too low and everything else is fine, just increase the resistance value. Otherwise, you change the frequency to get the inductor and capacitor voltages to both be high enough and to be different. We do not want them to be the same. So you're going to do this first. That's why I recommend you start with the 3 probes just so you can choose your frequency. Once you've chosen your frequency, you don't change it until you get to the end of the experiment. You make the 5 measurements that Aaron and I made, Andrew and I made, and then this one. and then you do your analysis. So you have, actually go here. You have this, well, the first question is down here. Why is the algebraic sum of the three voltages, resistor, inductor, and capacitor? Remember this here, the L plus R is measuring across the inductor. It's got a resistive and a capacitive and an inductive and a resistive part. So that's why I have marked it that way. Why is it not equal to total voltage? You need to answer that showing that you understand what we've been talking about. Then how is it possible for the voltage across the inductor and the capacitor to be larger? We just talked about that. Make a 1/2 page phasor diagram using this model and determine V sub R and V capital L. Calculate the current based on your voltage drop across the resistor. Then using that, calculate the value of the resistance in the inductor, the impedance of the inductor, well, reactance of the inductor, reactance of the capacitor, and discuss the relative sizes. You know, you can do that. Draw the phasor diagram now with everything. So now you're going to come back and now you're going to draw this phasor diagram. And please make the order the same. First, show the voltage drop across the inductor showing the resistive part and the inductive part. Then the voltage drop across the resistor. Then finally the voltage drop across the capacitor. It helps to spread things out. From this graph, you are measuring the length of V total and the angle. Those were two of your results. Then you're going to calculate that. Was the phase angle from in agreement with the ideal phase angle? What's the ideal phase angle? And what phase angle would you be charged only for the power you're using? Yeah, 0 is the ideal. Then you're calculating the apparent power and the actual power. The apparent power is I times V. Actually, if we want to be real cool about this, the correct thing for apparent power is I RMS V RMS, which is equal to 1/2 I peak V peak, or 1/2 R V R squared. So that's the apparent power. The actual power is going to be 1/2 R V R squared cosine phi. Then you do the resonant frequency part. So this last part, you've already calculated what L is, you've calculated what C is, so now you calculate what the resonant frequency is. Remember, we went through this. I'm not going to rewrite it because I want you actually to go and show how you get it. But you calculate what the resonant frequency is, and then you go from 1/2 the resonant frequency to 3/2 the resonant frequency in steps of 1/10 the resonant frequency. So I used an example with Andrew. Let's suppose that we had F0 is equal to 600 hertz. If F0 is 612 hertz, use 600, okay? Don't make life hard and say, well, I'm going to go 612, half of 612 is 306. So I'm going to go from 306 to 918. If it's 612, just go from 300 to 900, right? That 12 is not a big deal. And then your steps would just be 60. And so I have 300 hertz, 360 hertz, 420 hertz, and so on. And all you're doing then is you're back to one sensor, of course, and you're measuring the voltage across the resistance for each one of those frequencies. So now you're going to change the frequency and measure the voltage for the different frequencies. You're making a graph of the voltage across the resistor as a function of frequency, and then determining where the peak in that was. So like I said, if you make it a logarithmic graph, it should look something like this, and it's easier to find where the center is. And so that center of this is the experimental resonant frequency. And the theoretical is the one you got from L and C. And my 600 here was just an example. That's not your number. So there's a lot going on here. Do you have questions that you actually can mention now? I'm sure you have questions. Do you have questions that you know how to ask right now? Okay, we should have groups of 2. We have an even number. So break yourself up into groups, and let's get started. And let's get done before the snow comes.